In this video, we are going to work out the packing efficiency of a body-centered cubic metal. Now, just like we saw in the last video and in class, the packing efficiency is equal to the volume of the atoms that are inside of that cell over the volume of the cell itself. Okay, so again, we're just looking at how much stuff we can pack into this cell when we are configured like a body-centered cubic metal. Now we are going to approach this the same way that we approached the last problem. We're going to look at the geometry of the cubic metal. Well, we'll look at the number of atoms in the cubic metal, and we'll look at the geometry, and we'll see if we can't calculate the answers to both of these values. Let's look at calculating the volume of the atoms first, which is kind of what we did last time. All right, I'll slide my paper down a little bit. We'll do that down here. All right, the volume due to the atoms. Now, in a body-centered cubic metal, we have 8 1/8 atoms. Those are present at the corners of the cube. And we have 1 center atom, giving us a total of 2 atoms per cell. All right, so we have 2 atoms. Like we saw before, the volume of atoms is going to be treated like the volume of a sphere, which is 4/3 pi r cubed. We have 2 atoms times 4/3 pi r cubed, which gives us 8/3 pi r cubed. I'll close my parentheses there, for my volume due to atoms. Great. So I've got my numerator already. Again, we've got r cubed right there. We've got that variable in our answer, but it's okay. If we can figure out a way to write the volume of this cell in terms of r, we can cancel out the r's, and that'll be just fine. All right, so let's see if we can tackle that part of the problem, finding the volume of the cell. Now, volume of cell, go back up here, V cell is just the same as the volume of a cube, which is a cubed. We don't want to leave it like that, though. We need to find the volume now in terms of r. So if we look at a body-centered cell, let's see if I can pick this up here. Whoop. Here we go. Here's my body-centered cubic metal. In this case, I cannot just draw a line across the face, right? Because if I draw a line across the face, I don't have atoms touching. I can't make any statement about the length of that line necessarily that I would draw across the face. One line has got to intersect all of the radii of the atoms, okay? Hopefully that makes sense to you. I can't say how many radii long this line would be because I'm not passing through that center atom. So I got to figure out some other way to do this. Get my iPad arranged again. There we go. Okay, what I'm going to do instead is draw a line, draw a diagonal, a hypotenuse for my triangle that passes right through that center atom. It's going to pass right through the central atom here. So I'll start up at this corner that's closest to me, and I'm going to draw a line to that lower corner that's furthest from me. All right, so I'm passing right through that central atom, passing right through the body of the cell. You got to think kind of in 3 dimensions here. I'm starting at the front top, and I'm going down and back to pass through that atom. All right, so that's one leg of the triangle. That's going to be my hypotenuse of the triangle. My other leg is going to be down the side here. That's equal to A. And my final leg is going to be one of these face diagonals, okay? Now notice, we are still going to have a face diagonal, even though I just said that we don't want to draw that line necessarily, but it's okay in this case to have a face diagonal as one of the legs because we do have one side that is passing through all of the radii. So it's okay. As long as this is passing through all of the atoms and I can write this line in terms of the radius, it's okay to have this line right here. I'll show you how to work with having that. Okay, great. Now I'm going to call this diagonal that I've drawn here, this body diagonal, I'm going to call it y. All right, so y equals body diagonal. And I'm going to call this leg of the triangle that I drew across the face, I'm going to call that x, the face diagonal. Okay. Now, in order to solve this problem, we are going to use the Pythagorean Theorem. I think that's probably the easiest thing to do. So if you'll recall, the Pythagorean Theorem is a squared plus b squared equals c squared. For a right triangle, the square of each of the legs is equal to the square of the length of the hypotenuse. Sweet. So what I need to do, first step, is I'm going to use the Pythagorean Theorem to come up with an expression for x, my face diagonal. Now the reason I'm doing this is that if I was just to try to, come up with an expression for y, all of a sudden I've got a's and x's and, r's and all this stuff. I want to see if I can put x in terms of a, and then I'm going to see if I can put a in terms of r. Okay? I feel like that sounded really confusing, but hopefully it'll make more sense as we walk through it. Okay? So first step is going to be to try to put this face diagonal in terms of a. So let's see if we can write this. One leg of this triangle here, so notice I'm looking at a different triangle, not the red one that I've drawn. In order to write this expression for x, I'm actually going to be looking at this triangle down here. All right? Which is also a right triangle. So we can use this method. So in this case, I've got one leg is a squared plus another leg is a squared equals x squared. 2a squared equals x squared. X is equal to a square root of 2. All right, so I'm going to go ahead and write that on there. X is equal to a square root of 2. All right, awesome. Now I've put that leg in terms of a. Sweet. Let's see if we can work a little bit with y. Y, as we know, can also be written as 4r because this line is passing through all of the atomic radii. So we can say y equals 4r. We can also use the Pythagorean Theorem to say that y squared equals a squared, that's this line right here, plus the square of this side. And instead of writing x here, I'm going to write a square root of 2 squared. All right, you see why we had to find x in terms of a now? Otherwise, we would have had x right here, and then all of a sudden we would have a whole bunch of variables, and that would just be a pain, and we don't want that. Okay, so this is an essential step, is putting this line in terms of a. All right, so we continue to solve. Y squared is going to equal 3a squared. Y then will be a square root of 3. Y is also equal to 4r. So now, look, I can put a in terms of r. A is equal to 4r divided by the square root of 3. So a cubed, the volume of my unit cell, is 4r square root of 3 cubed. Notice I've got r cubed here. R cubed is going to cancel out here. So when it comes time now for packing efficiency, I take my volume of the atoms, 8 over 3 pi r cubed, divided by the volume of my unit cell, 4r over the square root of 3 cubed. And what I should get when I calculate all that out is 68%, well, times 100%, of course. 68% for my packing efficiency. The tricky part here, I think that messes people up a lot, is putting x, putting this face diagonal in terms of a, so that you then can turn around and put a in terms of r.